środkowy. Nie, вона що буде? Надо сейчас залізти.
Саме цікаве, що ви закрилися ті, що в мене не було. І навпаки.
Так воно... Я знаю, що я...
Hello everyone, my name is Marta Choluj and I am a PhD student from Wrocław University of Science and Technology, and today I would like to tell you about the importance of theoretical studies of these spatially confined atomic and molecular systems. So I will start by giving you a short overview of the theoretical studies of atomic and molecular systems in confined spaces, and after that I will present the results of two projects which we finished recently. The first one is about the electronic and vibrational contributions to the static electric properties of spatially confined molecular complexes. And the second one is about the influence of spatial confinement on the two-photon absorption response of lithium hydride. The studies of atomic and molecular systems in confined spaces have become a topic of great significance during the past few decades. The classic examples of this phenomena are the inclusion compounds, which are chemical objects trapped inside molecular cages of different topology. For example, in nanotubes or fullerenes, they are key structures in supramolecular chemistry, artificial atoms, and matter under high pressure. A constantly growing interest in experimental and theoretical studies on the spatial confinement phenomenon is especially connected with the fact that various physical and chemical properties of atoms and molecules within restricted spaces can differ significantly from those occurring in unconfined environments. Therefore, such systems can contribute to the development of many fields of science and technology. In our research group, we focus on the linear and nonlinear electric properties because they are particularly interesting and very important for the development of molecular nonlinear optics. It is also very important to note that experimental studies of the spatial confinement phenomenon can be very challenging. Therefore, theoretical chemistry can stand as a relevant source of information. However, let's look, for example, at a molecule embedded in nanotube. We have a lot of atoms here, a lot of electrons. So performing calculations using highly accurate methods can be very expensive and very difficult. Therefore, we need to use simplified models. And one of the most commonly used techniques to represent the effect of spatial confinement is based on the analytical external potentials, which are included in the Hamiltonian of an isolated system in the form of one electron operator. And one of the most commonly used potentials is the harmonic oscillator potential of cylindrical or spherical symmetry. And the physical meaning of the omega parameter, which is here and which describes the strength of confining potential, can be explained based on this simple formula. So when we calculate the total energy of a molecule in the presence of confining potential and without the potential, the difference between these two values will correspond to the exchange repulsion energy of this molecule embedded in a real chemical environment. So here we have the connection between our simplified model and real chemical situation. And the first project, which I'm going to talk about, is about the electronic and vibrational contributions to the static electric properties of spatially confined molecular complexes. Over the years, various analytical external potentials have been used in the studies of electric properties of spatially confined molecular systems. And in general, it was shown that polarizability and second hyperpolarizability decrease under the influence of spatial confinement. However, dipole moment and first hyperpolarizability can behave non-monotonically. However, in the vast majority of cases, only purely electronic contributions to the static electric properties were analyzed. But there is one very important paper done by Dr. Robert Zaleśny and his collaborators, and they studied the vibrational contributions to the electric properties for model linear molecules using the harmonic oscillator potential of cylindrical symmetry. And they found out that both electronic and vibrational contributions decrease under the influence of spatial confinement. However, the electronic contributions are affected to the larger extent. So we wanted to further investigate this issue and to verify this observation for more complex systems. So we chose two hydrogen-bonded molecular complexes, HCN-HCN and HCN-HNC. We modeled the effect of spatial confinement using the cylindrically symmetric harmonic oscillator potential. We performed calculations using the highly accurate coupled cluster methodology, and we used also the scheme where we decomposed our studied properties into electronic nuclear relaxation and curvature contributions, and we focus on the nuclear relaxation contributions because curvature contributions are usually smaller. So the first step in our procedure was the geometry optimization, and we optimized the geometries of our complexes in the vacuum and in the presence of a confining potential. We used two values of confining potential strength, 0.1 and 0.2 atomic units. And we can see here that all bond lengths decrease under the influence of spatial confinement. The largest decrease is observed for HC bond length in the case of both complexes, and such shortening of bond lengths was already observed for different molecular systems under spatial confinement, and it is connected with the deformation of electronic density distribution due to the Pauli repulsive interaction with confining potential. And such interaction causes the increase of the electron density in the internuclear regions of a molecule, or in this case of a complex, and this leads to the shortening of bond lengths. And here we have electronic and vibrational contributions to the polarizability and hyperpolarizabilities. And first of all, we can see that spatial confinement has really significant influence on the studied properties. And when we consider higher orders of derivatives of energy with respect to the electric field, the influence of spatial confinement is larger. For example, for the second hyperpolarizability, we have 50% decrease of electronic contributions for HCN-HNC complex when we go from 0 confinement to 0.2 atomic units of confinement strength. We also can see here that both electronic and nuclear relaxation contributions decrease under the influence of spatial confinement. However, electronic contributions are affected to the larger extent, which means that the vibrational contributions, the importance of vibrational contributions increases when we apply confining potential. And in order to gain insight into the changes of vibrational hyperpolarizabilities, we performed the breakdown into harmonic and anharmonic contributions using the perturbation method of Bishop and Kirtman. And we can see here that anharmonic contributions are quite large, especially in the case of HCN-HNC complex. And we can see here that both harmonic and anharmonic contributions decrease under the influence of spatial confinement, and in most cases, the harmonic contributions are affected to the larger extent. So the most important conclusion here is that both electronic and vibrational contributions should be considered in the interpretation of the electric properties of spatially confined molecular systems. And the second project which I'm going to talk about concerns the influence of spatial confinement on the two-photon absorption response of lithium hydride. So over the years, a considerable amount of experimental and theoretical work has been devoted to the design and development of molecular systems with large two-photon absorption responses. And there are some experimental studies indicating that spatial confinement can also be a very important factor contributing to the changes of two-photon absorption response. Because, for example, the enhancement of two-photon absorption response was observed for different organic molecules embedded between the interlayer spaces of clay minerals. So in our project, in order to analyze the influence of spatial confinement on the two-photon absorption response of lithium hydride, we analyzed the two-photon dipole transition between the ground and lowest laying excited state of lithium hydride by considering the values of second-order transition moment, which is fundamental molecular quantity that describes the two-photon absorption response. We also analyzed the two-photon absorption strength. For the comparison, also oscillator strength, which describes the one-photon absorption. We also employed the two-level model, which allows us to describe the second-order transition moment in terms of simple spectroscopic parameters like transition moment, change in polarity between states, and excitation energy. We also analyzed the bond length dependence of the investigated quantities, and we used the multi-configurational self-consistent field method and response function formalism. So here we have the results for second-order transition moment obtained using the response function formalism and using the two-level model. And first of all, we can see that the behavior of second-order transition moment is very non-monotonic. We have two large extremas here. And we also can observe that the values obtained using the two-level moment are significantly underestimated. However, the qualitative changes are the same, so we know that we can use this model to try to explain the observed changes. So let's look closer at those results. When we look at the experimental equilibrium bond length of lithium hydride, which is 3.015 atomic units, we can see that the spatial confinement causes decrease of two-photon absorption response of lithium hydride. However, when we stretch the bond length of lithium hydride, there is this range when we can observe a very significant enhancement of two-photon absorption response. So we can now try to explain those changes using the two-level model. So here we have the transition moment, excitation energy, and change in polarity between states. And the shape of this property is very similar to the second-order transition moment. And for the experimental equilibrium bond length, we can see that the observed decrease of two-photon absorption response is mostly governed by the decrease of transition moment and increase of excitation energy, and the enhancement of the two-photon absorption response in this range is mostly governed by the change in polarity between states. And here we can also see the oscillator strength and the two-photon absorption strength. So the changes here are very similar to those observed for the second-order transition moment. This is only the other way to describe the two-photon absorption response of lithium hydride. However, the interesting changes can be observed here because the oscillator strength also exhibits non-monotonic behavior with one extrema. However, in the whole range of analyzed bond lengths, the spatial confinement causes decrease of the oscillator strength. So the conclusions: the importance of the orbital compression of the spatial confinement effect increases in the case of highly distorted geometries of lithium hydride, because at distances larger than the equilibrium bond length, a substantial enhancement of two-photon absorption response of lithium hydride might occur. So I hope that I showed you that theoretical chemistry can give you some interesting observation about the spatial confinement effect. So I would like to thank my collaborators, Dr. Robert Zaleśny, Dr. Justyna Kozłowska, and Professor Wojciech Bartkowiak, and you for your kind attention.